Hey everyone, welcome to the Supercognition Podcast. In this episode, we're going to be talking through a paper titled On the Measure of Intelligence by François Chollet. This was published in November of 2019. François is a world-class software engineer and AI researcher at Google. He's also the creator of Keras, which is an open source library that is designed to facilitate experimentation with deep neural networks. It's currently integrated into the TensorFlow main codebase. François has also published Deep Learning with Python in 2017, and he's conducted two fascinating interviews on a favorite podcast of Zach and mine's called The Lex Fridman Show, which were both over the past year and well worth checking out. This paper sets out to identify the need for and begin to explore the attributes of a benchmark to general intelligence. In terms of a benchmark for general intelligence, Zach and I wanted to talk through some definitions. Do you want to jump into those, Zach?
Sure, yeah. So I think we were just playing around with some of these ideas that we want to discuss. Primarily, what is intelligence? And I think it's the ability to make models, and key to that would be, the knowledge or the information that's used to build that. And at some point, we'll want to explore some ideas from, information theory. What is information? But when you have information, which is what our senses are presented with, intelligence is the ability to assimilate that into models, which are compressed representations of the information that we have perceived. And then you've defined wisdom here as basically the policies that allow you to make good decisions to optimize for some goal, given those models that you've developed. Those are a few terms that might be helpful. I think intelligence is something that can be defined in many ways, though. We have a few quotes here and different definitions. Einstein defined it as the measure of intelligence is the ability to change. It's an interesting definition. Stephen Hawking, intelligence is the ability to adapt to change. I think Yosha Bach's definition resonates with me. Intelligence is the ability to make models. General intelligence means that a sufficiently large computational substrate can be fitted to an arbitrary computable function within the limits of that substrate. I think that really gets to the heart of what intelligence is.
Yeah, and in keeping with that, having information, developing knowledge, which is using that information to build models, including that intelligence of those models into wisdom, which we could say would be using those models to make good decisions, will ultimately allow a generally intelligent system to adapt to change that much more effectively. So if we're trying to condense all of those down into a single, concise representation of what we mean when we're talking about general intelligence, we could say perhaps that it's the ability to compress, to summarize, to correlate, to remix, and to make good decisions beyond a system's training data set. If I develop a chess-playing supercomputer that's really good at playing chess, as IBM did with Deep Blue back in the day, we can learn so much about thought from the exercise of using a tree search with a minimax function to just completely dominate the game theoretic space of chess. But that approach to developing intelligence in that system, the way I'm thinking about it, tells us more about the intelligence of the system's creators than of that machine system itself, because that approach to the development of intelligence in the system is highly context and state dependent on the domain of chess.
Right.
Machine learning, yes.
And that's the point of the paper, right? Is we don't want to just build a bunch of narrow skills. We want to build a general learning system, so something that can approach the world like a child and just learn over the course of a lot of experience, learn, a panoply of skills and develop those and mix them. And like you said, take that ensemble of narrow intelligences and combine them in ways to be able to, for example, reason by analogy, to take, to recognize when, for example, a skill in one domain correlations or applications in another domain, and to be able to hypothesize that maybe we can look at the problem through a different set of lenses and be able to, like, we do that all the time when we reason by analogy. We look at, for example, atoms using analogies of objects that we're familiar with in our everyday life, but we reason by analogy continuously, and that's a large part of how we innovate, is by taking different narrow forms of skills, narrow intelligence, and applying those to other problems that we want to reason over.
So how general do we think human intelligence actually is when viewed through that lens?
Yeah, I would argue not that general, right? So I think we're probably stuck in quite a local optima compared to at least what's theoretically, physically possible. We're intelligence constrained by the size of the cranium, when that's constrained by the size of the birth canal. And so, what is the theoretical global maximum that could be reached given an efficient computable substrate, given something like a silicon chip that has signal processing at something close to C compared to 150 to 300 miles per hour, which is roughly the speed that biological neurons fire. So I think we're just nowhere near the global maximum of what the general substrate, for example, of silicon, and there's maybe potentially other substrates. In fact, potentially we can form neural architectures that are purely photon-based, that have optical neural networks eventually. And so, like, there's this unknown ceiling of what the global maximum is, and then the size of that will determine its potential in terms of how complex the models are that it can develop and train through some form of search. Intelligence is fundamentally a search for models, and there are different forms of search. You can take permutations and do some selection process based on survival, which is of course the genetic or evolutionary approach, where you do permutations based on some interpolation or some between, for example, two parents, or some crossover, genetic crossover, for example. And then there are other types of search that are sometimes more efficient, but sometimes more prone to overfitting, underfitting, overfitting in particular, and sometimes, which is the gradient descent approach, which probably is not biologically plausible. Definitely, I would say not biologically plausible, and yet mathematically it provides a great way to traverse these models and measure, which part of the model is responsible for the loss, and then to take a gradient step in minimizing that loss function. But fundamentally, all of these models are doing the same thing. They're searching some high-dimensional space for some model that is accurately descriptive of an external reality that gives it prediction power.
And that's such an interesting point, because the higher dimensionality of that space implies that perhaps an intelligence which evolved in an Earth-based ecosystem, according to the fitness function in the game theoretic dynamic sense of survival, could be optimized for wildly different heuristics than perhaps a kind of intelligence that might first emerge through a machine-based language model, or through a foreign exchange trading algorithm, or anything along those lines.
Yeah, whatever. And I find those heuristics are very insightful, and we use them all the time, and there's times when they're very, very useful, because we don't have, for example, the computation to calculate the precise. For example, we use heuristics to catch a ball. The heuristics are basically run and keep the ball at the same eye level, and we can run without looking down and basically intercept the trajectory of something flying without doing any kind of calculation. And pilots use the same thing. When you're landing, you just keep the target landing spot at a fixed point on the windshield. I think heuristics are very useful, but they kind of give away the fact that our reasoning is based on a neural network, and it's going to take a shorter path if it can. But heuristics are just shortcuts. They're kind of simple rules that allow us to avoid spending energy. And it's not clear that we couldn't do a lot better than that with synthetic cognition, where we have potentially the ability to scale compute to trillions of times, in theory, hypothetical global maximum. So we could potentially scale compute to billions or of times the size of the mind. And so maybe we don't need heuristics at that point. Maybe we can actually globally model the state of the outside world or something close to it.
It's so interesting to me when I think of the number of independent minds, each running highly detailed simulations we already have running around on the surface of this planet. And it's so unfortunate to me that the evolutionary trajectory of these minds to date has been a world of competition between the organisms that power those minds as such.
But that's been the selection function.
Yes, exactly. Sci-fi has been talking about hive minds for quite some time now. But what we're describing in even the most elementary machine intelligence is the potential to parallelize essentially infinitely, subject only to the physical constraints of the universe, be they thermal, energy availability, etc., which means that if we have a machine which, let's say, operated at biological, chemical level clock rates and at human levels of intelligence, and we had 8 billion of those machines, they would automatically be godlike compared to the intelligence exhibited by any human available today. And when you add the vastly higher levels of working memory that we can essentially take for granted, and the vastly higher clock rates that we can already demonstrate, that to me really helps to emphasize how big of a thing it is we're conceptualizing here.
Yeah, and we're directly optimizing every subcomponent and submodule of intelligence, right? Which you mentioned discrete memory, for example. We have perfected discrete memory in SSDs and various types of memory arrays, and as opposed to the human mind, which of course is holding memories of discrete information and trying to keep and preserve those memories over the activation patterns of distributed neurons. And so obviously it's a much less efficient way to do discrete memory, and that is evident in hundreds of memory cognitive biases. And so I think, there's vast room for improvement beyond the level of human intelligence, and that's interesting, exciting. It means that we might be the bootloaders for AI, and we might not be the final life form, and we might be the Generation Z that's basically building our successors, which is an interesting. I think Sam Harris points out how AI is such an existential threat, and yet for some weird reason we don't think about it the way we think about other existential threats. We don't get all tense and nervous and fearful when we think about it. Instead, it's exciting because we're, in a sense, building a god. In a sense, we're building this super intelligence that is intriguing and is fun. And so, there is both concerns, right? Because I'm a natalist, and I think you are. We probably want the human biological consciousness to perpetuate and to continue its existence, but at the same time we're building a form of intelligence with AI with silicon substrates that it is impossible to predict at this point what the end game of that will look like, what that intelligence will decide. At some point, any sufficiently intelligent system, given any benign goal, you have the unintended consequences problem that you encounter, where any sufficiently intelligent system instructed to perform a benign goal will do so in a way that is not aligned with general human values.
The paperclip maximizer that swallows the universe example.
Yeah, exactly, right? And so the question is, are we on a trajectory that indicates we will likely quickly exceed baseline human intelligence and reach some form of general superhuman intelligence? And it definitely appears like we're on that trajectory. Just in the last couple of days, Google has increased state-of-the-art model size from 175 billion neurons with or parameters with GPT-3 up to 1.6 billion parameters with their new scale transformers or whatever they're called. And
trillion, yes, just incredible.
Just incredible, right? Because we've already last year we passed the human neuron count of 86 billion neurons, but now we're on a trajectory that in a few more years we're going to have crossed the human synapse count of around 100 trillion synapses. Give that another 2 to 3 years, probably, maybe 4. We'll see. I mean, it could always surprise us. And so, yeah, well, where does it stop? I was just actually looking at the benchmark for superglue, and the last time I opened up their benchmark page, the human baseline was number 1. And now there are 2 models that have surpassed the human baseline for superglue, which is the general language understanding evaluation benchmark. And of course, that was a response to the glue benchmark that was so quickly surpassed by, I think, BERT and other language models. And now you have superglue, which was a much harder challenge. But where's the next superglue? Where does it stop? And at what point do we just throw up our hands and say, yeah, the machines have won?
There's a great excerpt from page 8 of this paper by François. When we know how a machine does something intelligent, it ceases to be regarded as intelligent. If I beat the world's chess champion, I'd be regarded as highly bright. This interpretation arises from overly anthropocentric assumptions. As humans, we can only display high skill at a specific task if we have the ability to efficiently acquire skills in general, which corresponds to intelligence as characterized. No one is born knowing chess or predisposed specifically for playing chess. Thus, if a human plays chess at a high level, we can safely assume that this person is intelligent, because we implicitly know that they had to use their general intelligence to acquire this specific skill over their lifetime, which reflects their general ability to acquire many other possible skills in the same way. But the same assumption does not apply to a non-human system that does not arrive at competence the way humans do. If intelligence lies in the process of acquiring skills, then there is no task X such that skill at X demonstrates intelligence unless X is actually a metatask.
Yeah, so in reality, what he's saying is that intelligence is this cognitive function of interpolating between skills, because skills can be optimized for directly, and we know of ways to optimize for individual skills, as long as we have a supervised learning problem that can be formulated as take X's, predict Y's, and optimize over a loss function of L2, L1 or L2, so your loss squared, some kind of a mean distance function or something. We can optimize over that and learn a skill just through gradient descent. But here, what he's referring to is this metacognition of skill acquisition efficiency gains that don't require learning every skill without priors, but allow us to basically reason by analogy and take an ensemble of existing skills and kind of learn a new skill with increased efficiency, because we're combining and recombining various components and have this kind of a modular skill system, which is what we have as humans. We have a fairly modular skill system where, given a new skill that we need to acquire, we can combine dozens or hundreds of other skills in novel ways and use that combination to increase our efficiency, so we're not learning as if we had no priors, which every machine learning model today is typically randomly initialized with some parameter vector, and then it's learned from scratch. And so I think a big part of this paper is exploring the priors that we should consider, and which priors did evolution optimize for. Probably spatial, probably quite a few. I mean, probably it's probably hard to quantify. I would say that most likely.
It is. Page 26 of this paper actually takes a stab at it. I'd love to include that in our flow.
Yeah.
Cool. So there's a few different categories described here. And again, this is page 26 of François' paper on human priors, trying to understand the environment in which our intelligence emerged and the priors as driving forces in that emergence, and ultimately fundamental attributes of the type of intelligence that humans exhibit. Quoting from the paper here, elementary physics would be one of those priors. Humans assume that their environment should be parsed into objects characterized by principles of cohesion. Objects move as continuous, connected, bounded wholes. Persistence. Objects do not suddenly cease to exist and do not suddenly materialize, which is a really amusing flaw in current image classification systems.
But is that actually something that's been biologically selected for? Because I think object permanence, for example, is not something that babies indicate an awareness of until a certain age. I don't know what that age is, but we should get some developmental psychologist on here at some point to explore these things. But I've seen the studies where they test whether a child shows signs of recognition of surprise when object impermanence is violated, or object permanence is violated. You can obviously see that monkeys have a sense of object permanence. There's classic videos on YouTube showing that, but I don't think that newborns do. So it's interesting he's putting that as like a biological prior, when I think that's something learned in the first few months. But again, that would be learned when neuroplasticity is at its highest. And again, neuroplasticity is kind of a correlate of the learning rate, which it's interesting that, it's analogous to how humans learn faster when they're young. We typically start with a high learning rate in neural networks and then diminish that over the course of the epochs of the training.
That nature-nurture distinction here is a really interesting point. If we're talking about something in which developmentally human babies begin to exhibit surprise or lack thereof in response to a particular stimulus within months of their emergence as new beings into this world, just distinguishing between the role that their priors play and their ability to do any kinds of conceptual modeling from those priors to the world that they're beginning to interact with feels like a rather sticky question in its own right. I have this image of baby kittens who physically cannot see, for my understanding is the first several weeks of their life as independent beings in the world, when they're quite helpless and dependent on a nurturing mother. And I could see an argument in which human priors may not manifest for the first few weeks or months because of similar sensory fusion processing, executive reasoning considerations.
I mean, I guess there's probably architectural priors. I'm guessing that neurons have some kind of weight system that they learn, and I'm guessing that there's probably not a prior in the actual weight system of these neurons, because they seem to be rather heterogeneous in terms of the neurons themselves. They seem to be very homogeneous and very similar in terms of their structure, and so I imagine that the neurons don't have priors in their weights, but probably some of the cortical columns or some of the architectural things would have had biological selection priors priors in their biological architecture through the selection process. So whether that would be just the different regions of signal processing, for example, the visual cortex, the auditory cortex, I would imagine at that level, I would imagine that we would have priors. I just don't know if there's some kind of a weight system in the individual neurons,
That's a really interesting point. One of the priors described in the list from this paper would be elementary geometry and topology. And we, of course, have large, multiple self-reinforcing systems of gray matter which optimize for topological processing, spatial relationships, pathfinding, navigation, even to the degree that building memory temples can help us remember arbitrary information by encoding it and correlating it with spatial and temporal structures. The fact that our brain has hardware optimized for topology, to me, feels like a really useful way to understand what we mean when we say prior in this context. Whether there is an initialized neural weight, there's certainly initialized hardware ready to start learning those weights from direct emergence into the world.
Correct. Yeah, and I think Yosha Bach even commented on that and said when you see a child, a 2-year-old, taking a piece of paper and folding it and pushing a pencil through it or something, right? What they're doing is they're proving complex theorems about topology and manifolds and spaces and, maybe a torus or something. And that is something that I think they learn, but they have an architecture that has been selected for that has that is very conducive to that learning. And so I guess the question with this paper is, can we measure a factor? Like, can we create a scalar loss function that allows us to quantify the skill acquisition efficiency of a system, which is a meta attribute of its intelligence? Well, it's like that's the intelligence that we want to quantify, which it's not the same as what an IQ test. Well, I mean, maybe it's the goal of an IQ test would be to test something like that, but it's not an easy thing to measure because of its very nature. So obviously this is one of very few papers that are actually trying to look at, how do we quantify that? And I think the cool thing about this paper is he actually proposes some concrete ways to go about measuring that, including what may be the first data set and benchmark to actually evaluate skill learning efficiency on, which is his ARC data set. And I'm quite excited about the next few years. Will we see increased efficiency on this data set? Right now, I think we're at, I think we're at about 80%, which is substantially improved since he released his paper from what he had been able to do, I think. But, it'd be cool if we could get to, so it's actually an 80% loss. I believe that's only 20% that are able to be solved right now. So it'd be cool if we could increase that 20% to, something like 80 or 100% in the next few years.
The trajectory things are currently following gives me much to hope for.
Yeah, and the implications of that. So dive in. Yeah, go ahead.
Let's really dive into this ARC data set. The specific classes of problems that it currently contains include dots on grids, so visual information processing, with specific tasks such as matching patterns, mirroring, denoising, object persistence, simple two-dimensional physical simulations where perhaps we could have dots that are moving between frames and should be reflected off walls, things of that nature. And the significance of these types of tests are that the abstraction and reasoning corpus dataset is interested in separating the skills which can be bought by by a degree of training input with the actual capability for abstract reasoning, which would be a function exhibited by a more generalized form of intelligence. So for example, if there's a particular pattern that I can code an expert system to match, we're saying that's not intelligent. Whereas if I can allow a system to start learning from training data set and begin recognizing patterns and running its own expected physical simulation outcomes when the dots start moving between frames, that would be a much higher level of intelligence because it's actually going to be developing a simulated model of the physical reality represented by those moving dots.
Yeah, I mean, this makes me think of some some of the heuristics we probably use for this type of perception in our neural pathways. And I just in the last couple of days saw some visual illusions that appear to be moving just using color, and they really appear to be rotating, but they're not. They're static, and it's just the color changing.
That's a great example. So many of those visual illusions play with our mental expectations of squares being perfect squares, windows always being rectangles, the white space
primitives. These are the geometric primitives that the mind uses and compiles. And again, heuristics are great because they do increase the energy efficiency of the brain, right? Which runs on only a few watts compared to, actually, I don't know exactly how much it runs on, but the brain is quite computationally efficient, energy efficient compared to our current deep learning systems that require a lot more power. You look at the power of these data centers compared to a human brain, and the number of compute cycles that they can model. But yeah, and I think one of the interesting things about this ARC data set is that it's not something that's very approachable from a traditional machine learning standpoint. It doesn't lend itself to optimization, which kind of is in the same vein as the work from Jeff Clune that we explored in our last call, where we talked about the deceptiveness of loss functions. I don't know that there's any way to use gradient descent to search for a solution to these ARC dataset problems, just simply because in many cases it requires like discrete memory, but it also is not formulated in a way that's very differentiable. So differentiable problems are easier for machine learning right now, but what we're looking at in the ARC dataset are problems that require domain-specific knowledge and kind of a search over probably a tree-style search. It's much more akin to program synthesis, and I think we need more benchmarks in program synthesis. It's much more akin to going from an input to an output, and then instead of optimizing for a model of composable function approximators that can be stacked to predict that output, what you're looking for is something that constructs that output as an object that it iterates over, and it does that through searching for a program. So it's searching in the space of computation rather than in pure pattern interpolation. And I think that's very exciting. I think there's been tremendous progress in this program synthesis world, and I think that there might be some combination between, for example, GPT-3 and the code synthesis that it's able to do, and maybe combining that with some sort of a decision tree or search tree structure that would allow it to function sort of like AlphaGo or AlphaZero, something that's using the search tree to estimate the value, and then using the generator to kind of create the branches that can be explored in that tree. So I think the ARC dataset is an incredibly valuable contribution to the machine learning community's pursuit of AGI. I think it's going to be one of those benchmarks that we will be measuring against for years to come, and I think that it's framed in a structure that's conducive to being expanded with much more data. Right now we have a few thousand examples in the ARC data set, but we could easily increase that, and I think it's a great model that could be applied to other types of. I think the same model you could almost take papers with code and look at their 3,600 benchmarks and imagine creating an ARC dataset type benchmark from 3,600 different benchmarks and all of those different data sets. Just think about this idea of a meta-learning system that's attempting to it's looking at the efficiency of skill acquisition, and OpenAI Gym did something similar, but for reinforcement learning. I think we need more dataset ensembles, benchmark ensembles, more of these. The whole point of the ARC dataset is you only have a few training examples. It's very analogous to it's basically few-shot learning, right? But it's few-shot program synthesis learning is what it is.
And as exciting as that idea is, I think it's worthwhile recalling the perspective that general intelligence may not be a single pinnacle of an ultimate reasoning system, which is a parallelized implementation of a single fundamental process. It may be much more useful to analogize general intelligence as an ensemble of dozens, hundreds, or even thousands of highly domain-specific narrow intelligences, which have been self-trained to solve particular problems, and in which the generalizing system can identify those problems through more abstracted generalized reasoning and imply the specific instances of specific intelligent systems to each of them.
Yeah. Yeah, and so, I mean, this paper, along with Jeff Kloon's, is in this vein of asking the question, what is the path to general intelligence? And I think this is the most fascinating question any mind could entertain and consider at this point in history, this epoch, where we are, for the first time, seeing that mechanistic systems, Turing machines, can outthink us at things that we, in our anthropocentric arrogance, often considered, or prior to this, most people, I think, considered human intelligence to be the pinnacle, and I think that's always been arrogance, right? To look at our intelligence and our world as if we're in some privileged reference frame, and I think we're not. We're nowhere near the intelligence. A few million years ago, we were probably as intelligent as apes, and so the question is now, since we're able to navel gaze and ponder our position in the universe and explore outer space and explore the quantum physics, where are we going to are we going to end up creating a life form that is on a new substrate, more intelligent, and maybe a more interesting life 3.0, right? And that's the point of that book by Max. Highly recommend Max Tegmark's book on that. And he defines intelligence as I don't know if we covered his definition. He defines intelligence as the ability to achieve complex goals or arbitrarily complex goals in a wide range of circumstances. And
it seems that each of the definitions we've explored either emphasize the ability to build models or imply that ability and ultimately use it to execute a successful strategy for survival or whatever the fitness definition would be.
I think it's helpful to just differentiate between those and not conflate them. And I recognize that they are two separate functions, right? One function is, and yet they're very correlated and very related, right? One function is the ability to model the world, and the other function is the ability to navigate that model towards some kind of objective that you want to optimize for. And we see various applications. For example, I mean, you can imagine an analogy of building a map and then using the map to navigate to some kind of a destination. You could use something like actor-critic. You could use the same analogy in terms of like a generator or discriminator, right? One is generating this model and one is discriminating or using it. And I think there's all kinds of ways to look at those. They're very synergistic, and I think that you need both capabilities. It's not clear, sometimes what the difference is because they both are making models. One is making a model, and one is making a model of how to use that model to navigate towards an objective.
This feels like the classic distinction between what we might call intelligence and wisdom. You can both know what to do, and you can actually do it. And those are two very separate things.
Yeah, it is. And it's a fun challenge.
Indeed. Well, we've just covered a lot of ground here. There's a few more topics I wanted to explore. I think it's worth diving into a really high-level overview of algorithmic information theory, since this paper treats it so beautifully. The idea of algorithmic complexity, generalization difficulty, situation space. Algorithmic complexity as such, I love to think of it as the length of the shortest possible program that, given a particular problem, can output a sufficient solution. So if I need to actually output a phone book of real people's names and addresses, I might need to understand how postal addressing schemes work. I might need to actually know about the location of tens of thousands of different human beings. Whereas if I just need a body of text of a similar length and pattern, I could probably write that in 2 lines of Python.
Right.
So when we're trying to understand the algorithmic complexity of any problem, it can be really useful to think of this in terms of the shortest program that can solve for it successfully.
Absolutely. Yeah, and that idea of the shortest program, I mean, this gets into what is the information content of something. It is the shortest thing it can be compressed to. It gets into this idea of overfitting versus underfitting versus an optimal fit. And the idea is that you want the most parsimonious or the most parameter stingy model that can fit your data with reasonably low loss, right? And you're actually going to have lower loss on that parsimonious model when you go to run it on your test set than you will with an over-parameterized model, which can overfit to anything. I think the human brain is over-parameterized, and that's why the human mind can believe in any idea, and you will find people that believe in the craziest ideas because they just simply overfit to those ideas, and they create unlimited numbers of special pleadings, and the human mind can overfit to any belief or any belief system.
So is this a natural consequence of a necessary architecture for survival in a changing world?
Yeah, I think the idea there, though, is that we want the most parsimonious model. In other words, the most parameter stingy model that sufficiently models the data. And that's the basic process of Salmonov induction. Salmonov induction is basically a theory of inductive inference based on Bayesian use of priors and posterior probability distributions, where you I mean, it's non-computable, but it's like theoretically the globally optimal, given unlimited compute budget, right? It would be the globally optimal mechanism to search for models, and it's based on Bayesian inference combined with taking the shortest available programs for anything.
And closely related to that would just be the concept of generalization difficulty. When you're trying to understand the degree of difficulty associated with generalization in a particular domain, I like to think of that as the difference in which the optimal behavior for any given real-world situation you need to behave in, and the degree that could differ from the optimal behavior in your training environment. If we're always trying to rotate images of dogs 90 degrees, that's going to be very low generalization difficulty. Perhaps if we have to recognize any image, find the horizon, and then figure out which way up should be, that would be a much higher level of difficulty.
Yeah, it's hard to quantify some of that, what that generalization difficulty is. I mean, I guess the point of this paper is that right now generalization is just hard to measure, and so I think it's exciting that we have kind of a data set that allows us to benchmark different approaches to generalization.
I would love to shoot a dedicated episode on Shannon information theory. There's so much more ground to explore there.
Absolutely.
Well, what else do we want to touch on for today's conversation?
I don't know. I think we've covered a lot of fun ideas. I highly recommend that everyone listening to this actually read the paper and take a look at the data set, actually play with the data set. There's a web app that allows you to interactively solve these ARC challenges yourself, and they're actually quite easy for a human to solve, but surprisingly difficult for any kind of machine learning algorithm today to solve. And so it provides a really, really good benchmark for the next few years for machine learning community. I think in particular the programming synthesis subset of the machine learning community will have a great new data set to work with for few shot program synthesis, which is what this is. I think it will go down as one of the very influential papers of the last year or so. Yeah, 2019, I guess. So November, just barely over a year and a couple months ago. But I think it will be looked at as one of the influential papers that kind of gave us our first data set for benchmarking general skill acquisition efficiency.
Absolutely. Well, I think that pretty much wraps it up for today. Thanks, everyone, for joining Zach and I in this exploration of On the Measure of Intelligence by François Chollet. Be sure to like, follow, and subscribe wherever you get your pods.